So there is a, here I'll do desktop. Oh wait, here I'll do that. So I'm sorry about that. So, but this is the life in the real world, I guess. Okay, so do you have any questions? Any? I did put an assignment out there for next Sunday night. For some really weird reason, instead of putting it at midnight, it puts it at 11. I don't understand that. Okay. I'll go ahead and draw the book up. Just as a fair warning, we may be not holding class today because and you probably don't want to get too close to me. I don't have COVID or anything because I've tested for that, but I've got something. It seems to be getting worse by the hour, so. Okay, wait a minute. I didn't want to go there. I wanted to go to the textbook. Where did the textbook? There it is. Okay. All right. So, so we talked a little bit last time about this thing and the triangular loads. And I'll just use this one and then I'll jump to the next section. So here's a case where there's a beam and maybe he's stacked a lot of bricks, but in any case, it's attached to the wall. Oh, you can tell it right here, but you can also tell it right here. Stacked a lot of bricks and then a smaller stack. He's put his coordinate system here. He has also used 9 meters, feet, whatever. He used a different thing. What he did over there is he calculated this 800x, and it's Pascals. It's 0.2 meters deep. So when you turn it on its side, the 0.2 times the 800x, there's an x right there, ends up being the weight per running foot. Running meter. The reason I say that is because I have spent a lot of years in construction, and they always say linear foot. That's what that means. It's running out there a linear foot, but in this case, linear meter. So every meter you go over, you have more bricks, so to speak. On the very right end, although it doesn't make sense, but if you put in x equal 9, you'll get this number at the very right end. The reason that's beneficial is you have that height times this distance divided by 2 is the area of that. And that area becomes 9 meters times that divided by 2 becomes the weight of all the bricks. And so what he does, he of course has that there. Then he goes down, excuse me. You'll see the 9. I brought a mask just in case. The 1400 half. So that's the weight of all the bricks. Now the key is it 3 foot over or a third over? And you get that from integration. Now, I don't know that he does the integration, But he says the line of action passes through the centroid of the triangle, which is the weight diagram. It doesn't have to be triangle. In other words, if you had a weird function like this is weird, and then you found, imagine if this was a metal plate and you found the centroid of it, essentially that's where the weight goes through. The centroid of this area. How do you find the centroid? Technically, that's chapter 9. However, he's already told you that, and that, when he had the triangle, he was doing x, if this is x, times f of x dx, however many x's this is from 0 to, say, L. So what you're doing is you're taking a little force diagram, and imagine, if you will, you're trying to balance. Now imagine this triangle is a big chunk of metal, and you're trying to put your finger right here. Here's your finger, and there's your other fingers, and here you are, and you're trying to balance this thing here. So there you are, balancing this on your finger, and you have to balance it at the centroid. So if you're trying to balance something, you actually can locate the centroid. It's directly above wherever you're trying to balance it about. Weird looking person, but what are you doing? You're doing this. Now, this is an area. So this is leading to, and this is part of what really bothers me about some of this, is that technically chapter 9 should be way back before this. If you think about an area, x bar equals integration of, what is this function? That this is the area under the curve, dx. So then you take this, that's the location of the centroid. Because what you're doing, what you'll find out in a second that he does, if he does it here, is you take the integral with that x on there. Then you take the area, which is the force, you slip it under, and you'll find the x, that's the location of the centroid. Formally, this is formally done, or it's purposely done in chapter 9. All of chapter 9 is that. So they're leading you to this, but what this course actually should have, it should have little math blocks that you take before you start doing things in here, because then it makes things seamless. You could do integration areas and vectors and some stuff like that, and then you could start. This would be cross products, dot products, things like that. But so what happens is he probably just basically, he doesn't do either one. But I think we did that last time. So let's find the location of this, and as a matter of fact, we could do that, or we could go straight to the problems. Okay, is it here, or do I go here? I think, was I already there? I was already there. Okay, there's this. How do I do? Okay, is it student view? Okay, here's the student view of the thing, and for some reason it clips part of it on the overhead. So let me line it up. Okay, wait a minute. Okay, this is this one. Let's see. This is the standard view. Data view? That's this. No, this is this. Okay, that's what you see, right? Do you see that? Is that what you generally see? So he's got all this. It's kind of, if you had a bigger monitor, you could see it all. Excuse me. It says begin by finding the equivalent resultant force and moment at point A. So what you're doing, I'm really sorry. I did bring sorry about that. What you're doing, of course, is you're going to move this, and this all to A. So I don't know what P1 is, but he's got them all listed here. So you could say, I'm going to put P1, I'm going to put, that other one's P2, and I'm going to put P3 all there and add them together. That's okay. But the next thing you got to do is you got to take the equivalent moment that's created by them. I don't know which direction it's going to be. Maybe it would be that way. I'm going to guess it's going to be that way. So I'm going to have a component pulling this way. This component is not going to produce any moment. This one will. So this will be, I think that's the 3. 3/5 of P. I think that's 3. You got L and L. So what you're going to have is the equivalent moment's going to be L times P2, L times P2, then 2L times P1, plus 2L times P1, and then I can't see what that is. I think that's a delta Y. Yeah, I don't know why who did that. Oh, now I see why. So he could force you into saying this is 3.5. This delta Y is 0.2. So you can find this distance as a number, and that distance I'll call delta. It's going the other way. Delta times 3/5 of P3. So essentially you're going to move this force to there, but when you move it, you have to also put a little moment. So by moving it, so if I move P1 there, I've got to add this. Then if I move P2 there, I've got to add this one. And then if I take this force and move it to there, I got to add that, or actually subtract it. And that's what you're doing through that. Does that kind of make sense? So it's kind of like, in a simpler form, it's kind of like this. I meant to draw that line the other way. If you break it down, and I have like 10 pounds, 5 away. This is the same thing. Yes, now, I can take this 10 pounds and move it straight down, and we're fine. So I can do this, but now I want to move it over here. And if I move it over there, I can put that 10, but I also have to realize that this thing is twisting this thing, and it turns out that it's 10 times 5 is how much that moment is producing. So again, by moving them up and down, that's fine. It's when you move them over to the right or left with this one. When you move it over to the right, you have to say, hey, wait a minute. If I move it there, I have to compensate by realizing that the fact that it's way over there is making it kind of torque this way, or in a static sense, it's creating a moment like that. So in essence, that's what you're doing. Move them, add a moment. Move them, add a moment. Move them, add a moment. And then you've moved all your forces to whatever location that is. Why do you do that? You do that because you've got the ground here attached, and guess what it does? The ground is pushing back up 10, and it's supplying a moment of 10 times 50. So at this connection here, they have to be equal or opposite. What is that? Newton's zeroth law? Every action has an equal and opposite reaction. So here's the 50 and the 10. Well, the ground supplies 50 the other way and 10 the other way. Now, some people will take this and then they will put it right here. And they'll say this. Okay, here's this and here's this. Now, that's legitimate because that's still equilibrium. But then in statics, what happens is a little bit, and this is the part that I find so intriguing, is if you just leave the 10 out there and the 5, then you can sit here and say this. And that's what happens more often than what we're doing in this section. So by him moving it, it's okay. But this is what actually happens, because this is now the free body diagram. The fact that you have freed the body, the structure, from its supports, and then you put the equivalent load on there to make it so that it doesn't move around. So this section is a little strange to me, given the fact that we've talked about free body diagrams a little bit, and then we go back to this concept where you're doing the free body diagram. So to me, it's more natural for me to do this. The problems in this section are a little strange like that, but I mean they're still worth something. And so they're not bad problems or anything, don't get me wrong. But if I saw this immediately, the first thing I would want to do is put the reaction loads on the blue structure so that it would remain. I would do this. I would say AX, AY, in the moment at A. And then I would go ahead and seek to find those 3 terms from this. So, and that's what you're going to be doing more naturally later. So 11. Okay, calculate 2 forces, that and that, in 2 moments, the 1 and the 2. Act in calculate the sum of the forces in the x direction. Oh, okay, that's simple enough. Part A. Part B, calculate the sum of the forces in the y direction. That's simple enough. And then calculate the magnitude of the resultant force. Okay. Calculate the direction of the result. So all you're doing is you're just, since he gave you this number, that number, and this number, and it's still clipping part of it. Man, this is really weird. Here we go. So all you're doing is you're taking the x component here, you're taking the x component here, you add them together, and that's, I guess that was part A. And the part B, this one, and this one. And then in a second, you've got to do the moment. No, wait. Calculate the direction of the result form. Given the, okay, that's basically adding those 2 together. Okay, calculate the resulting moment about point A. Let a positive moment act counterclockwise. Okay, at least he's following typical sign convention. And that is the cross product comes through. It defines a right-hand coordinate system. Okay, so if you do that, he said it A, so all you're doing is you take plus value here because it's going in that direction. This is going the other way, a minus value here. Well, A actually has, okay, so then you're taking whatever this number was times 2 meters and whatever number that was times, now see that's 3 meters. Now, technically, I should have done them like that. Oops. And Okay. So in this, since he does not give us this width of this thing, we're going to assume it's 0, and that point and that point. In other words, this force and this force produce no moment about A. And he even wrote A on the top, so he could have indicated that that's where he's interested in, at the top of this beam. More not likely than not, most people are interested down there. And so all you're doing is you're just filling that out.
And then, no, that's all there is there. 3. Some guy is pulling on this. What is the M? Okay, hang on. I can't make it go. Okay, well, I guess I just got to. What is MF? The contribution of the moment about point made by the X component of the force at point A. Gosh. There's A. There's the guy A. What MFY contribution made by the Y component. Okay, so what he's actually, see if, oh, here we go. I can just slide it to right there.
So essentially, what you can do, okay, this is strange, but not too strange. Okay, transmissibility means I can move this back to here. Okay. And I'm assuming, okay, okay, let me slide down and see if he tells us
More information.
Okay, so it's 60 pounds. This distance is off the ground by 5.5. This distance is over to the left 14. So this is 14.0. And this, for some reason, is 5.5. Now what that does is that gives you the dimensions for you to break down your components. Here's what I mean. Sorry. If this is that and L is, it's got to be in there somewhere. Oh, L is 12. So this is 12. Then that means this distance, and I'm just going to say like this, 12 minus 5.5. And this distance is still 14. Now, if you want to, you can find the length of that rope, and then you can break these components down. He said this was 60 pounds, and so you can say 60. But the component here, let's see, okay, if it was 6, this would be 6. In other words, if this number were 6, it'd be 6. So this is 6.5. Is that right? All right, 12 minus 5.5, I think that's 6.5. So that means this component, this force, that thing, is actually 6.5, or 6.5 over the magnitude of the length of that rope, which ends up being 6.5 squared plus, doesn't look to scale, does it? Do I get that wrong? 12. Well, wait, now that makes sense, because if that's 14, that's 12. Did I read that right? X is 14. So there's nothing to scale here. So I think that it's 5.5. So that 5.5 is almost the same length as the 14, but 12 is much larger than 14.
It's okay. Did I see all those right? Anyway,
well, and then there's the 6.5 and then 14. This is weird to see that. And this one is 14 over the square root of the same stuff. Now, he asked the question, Interesting question. What is MFX? The contribution to the moment about point O made by the X component of the force when. What is MFY? The contribution to the moment about point O made by the Y component of the force. Now, interesting. It's really strange. Oh, did he give us an angle? Oh, it creates an angle. Of course, it always creates an angle. Now, this is a kind of a trick question because I could see where you would have this, right? But if you translated the load back here, what does that produce moment about here? But yet if it's out here, it does produce a moment. So it's kind of a trick question. Can I move it? Can I not? That would be interesting. I think I'm going to let people answer that and just kind of see what they get, and then I'm probably just going to say everybody gets full credit. And there's a button that I can push like that. Because one person is going to say, hey, there's 5.5 times 14, and that would be the moment. Hey, wait a minute, but transmissibility, did he state that it has to be applied at A? Okay, so think about this. If I move this back, and I consider it here, the moment is actually 12 times this component. But if I leave it here, the moment is this times 5.5, and this force times 14. It's going to turn out that it's going to supply the same moment total. So him breaking it apart, some people are going to answer it one way, and some people are going to answer it the other way. They're going to move the load. So he needs to be very specific. Contribution made by the Y component at, he does say at point A, but the force at point A. What is the total moment due to the force? Assume the moment is acting counterclockwise. Oh, okay, positive. Where's the moment acting negative? Okay. I can see where this could cause trouble in the solution. So don't get too upset if you get it wrong. And there are many times that some of this is, looked at that way.
I'm interested to see, part B. View all hidden parts. Using the principle of transmissibility, the force can be slid on the line of action from point A to any other point in the sense. What point along the line of action would significant or simplify the calculation of the moment? I can answer that one. The magnitude of the total moment due to the point E. Yeah, figure 2. So I guess if I click that 2, it talks about that figure. So we're talking about that for a second. So, sorry.
Okay, so this one is okay. Don't get too upset about other things. Get awry. I think maybe on this part he's splitting hairs, but he should specifically say, but I could see where it would be viewed differently. Okay, then he says,
the C says, okay, the force creates an angle with the shed. Oh, that's a shed. Okay, that box is a shed.
Now, I guess he's implying you could do something like this. You could slide it to the point where you did this. Then this part would not supply a moment about O. This part would. So if you could add this extra distance take only this component, you should get the same answer. If that makes sense. So, I don't know.
Geometrically, there are little tricks like that that you can do. Yeah, we don't need to. I don't need to really answer anything. Okay, in figure, F is equal to 90. I'm sorry, 80. Part A, there is only part A. Determine the moment of the force about point O. Point O is way over to the left. So,
on this one, for me, he's got 45, which that's kind of convenient. And this is actually a distance of
100 millimeters. Can you move that up? It doesn't allow me to move that bar up.
So this is 100 millimeters. So essentially, you could do this. There's a couple of things you could do. You could work it the hard way and try to figure out that distance, and then you'd only have that one. Because this one, so you can move the load down here. I don't know that it's worth finding out the geometries there. To me, I would just do this and do this. Then I would take this component and slide it all the way to effectively here, which means I would basically, in my mind, I wouldn't have to actually do that. I could just find that vertical distance, which actually is nothing more than 200 over square root of 2, because that's 45. And then I would take the fx component there. Then what I would do with the other one, so in your mind, or you would basically move it to about right here and find that distance. So this would be 100. This would be, again, 200 over square root of 2, and that'd be 100. So essentially you're breaking it into two components, sliding the components along the line of the action, and then working the moment there and the moment from there. That's the easiest thing to do. Sometimes it won't take you long before you're not actually drawing the transmissibility movement. You're just trying to find the perpendicular distance. So you'd find it out here, and in your mind you wouldn't draw that, but in your mind you kind of know you need to figure that distance because it's perpendicular to this. And this line is perpendicular to that. So then he just wants to know the moment. So you want to know that comes this, and then this goes this way, but the other one goes the other way. So you have to subtract it. Does he tell you determine the moment of force and neglect the thickness of the memory? Okay. I guess the moment about. So I'm guessing because of that, he's not designated whether he wants a minus or a plus here. I would go ahead and just put a plus. But I know, there's going to be a direction. 60 degrees, I'm betting that since this component is going to be larger than that, and that being down here further away than this, I would assume that the total moment's going to be going that way. This would be that times this distance minus this times that distance. So, so I would enter a positive because he did not tell me that, and I may be wrong, but he did not tell me. Let me just do this. I mean, it doesn't count off for me. It tells me it does.
Oh. Okay, now I stand corrected. That is.
So my question would be, and I see this, and he's put in a minus. So my question is he assuming this throughout? And if he is, that's okay, because this is legitimate. This is from a mathematical viewpoint, a moment that is counterclockwise is in fact positive from math, because we always draw the x this way and the y that way. If some crazy person wanted to draw it this way, then I cross j be the other way, but we don't do that. Generally we do it this way. So this is a positive right-handed coordinate system. And so that places that as being positive. And in fact, maybe that's what he's doing. So I stand corrected. He put a minus sign there. He should describe that either here, or maybe he assumes throughout the text that this is the case. And if he does, kudos to him, because that's mathematically correct. So, there you go. I like to see something consistent throughout
The book. I didn't get any points for that. It took away all my points. Well, there is a part B. Okay, two men are exerting 90 and 50. And here's their little drawing, which I can't make it bigger, which I wish I could. Determine the moment of the force about point A.
That's kind of convenient because essentially, okay, the guy's pulling here. But the part that he's pulling down, this part of this component, supplies no moment about A, because it doesn't have a moment. If I can translate it along its line of action, it sits right on top of A. So the moment is only 12 foot, comes this component. Likewise, the guy on the left, at B, he's 45 degrees, so he's got a component going this way. He's also got this component going straight down, and it looks like it's 12 and 6 to that component. And so that's his moment. Now, okay, enter positive value if the moment is counterclockwise and negative. So he states it here. He should have stated it in the other. This is the correct thing, like I was saying. That's X, Y. That's a plus, so that's okay.
He will make me livid if he ever changes that. I exist livid anyway, so.
But I'm too tired to do that, to talk about that anymore. Okay, determine the moment of force P about point A. Okay. Wait a minute. So this is P. Is the other one F?
Oh, it is. So he wants to know the moment of one and then the moment of another. Which way will the pole rotate, clockwise or counterclockwise?
Okay. Well, if it's buried in the ground, it's not going to rotate at all. You should say, which way will the pole tend to, I'm being particular, tend to rotate. Want to rotate, but it may not rotate at all. Okay.
I can see why you asked that, though. That's okay. Okay, this is just a bunch of, okay. Gosh, that's a confusing drawing. So what he's got is a point laid in the XY plane, and then one that's directing towards B. So if you wanted to find, okay, so if you wanted to get from point A to point B, you would go along here, and you'd go along here, and then right there. I'm assuming it gives all those. So this would be dx and dx. So f, or here, let's do it this, a vector r that goes from A to B
is going to be equal to, I'll do the x's first. Here are the x's. So it turns out I go backwards. dx1 and backwards dx2, and then I go I. Where's my y? I go out this direction, I'm going positive. dy1 j, and then I go up dz2, sorry. Where's the dz1? I guess that just because you have a dz2 doesn't mean you have to have a dz1. So once you have that, because the magnitude of the force is that. So the next thing you do is you create a unit normal by putting the RAB over its magnitude of RAB, and then you multiply it times 200. Okay, once you do that, moment of a force about a point in 3 dimensions. Identify the components of the position vector from O to A. From O to A. Okay. So what he's going to want you to do, he's doing something different. Here's what he's doing. He's going to want you to define this. And then obviously the next thing he wants you to define is this. RB, RA. So R, A, vector to here, plus R, A to B is equal to RB. And so if I walked here, then walked here, and then somebody else is walking, I guess they'd have to fly because this is in 3 dimensions. So we'd still end up at the same place. What I did is I started at A and walked to B. So it's on RX, RY, RZ.
Then the next thing he's obviously going to do is going to want you to walk to B. Oh, identify the components from A to B.
So you do it this way, in order this way. You're going to get the same thing.
Then the next thing he's probably going to want you to do, find the normal. Oh, okay, he doesn't want you to find the normal,
but you have to find the normal and multiply it times 200 or whatever number you have. And that'll give you your components. Now,
does he ask for a moment anywhere? Calculate the x component of the moment vector due to force with respect to point O.
Okay, this is why he wanted to know that. The reason he wanted to know that is this is the point, you draw a vector. So if you want to know a moment, it's R cross F. Now this actually becomes A, and this is the F that you have. So it's kind of like this. If you want to know the moment about any force anywhere, draw any vector to it, and then do the cross product. So that's what he's wanting to know. That's why he wanted to know A. And then you have to know this in order to find the unit vector, and the F in my case becomes 200 times the unit vector to this AB. And so
and so that's pretty much that. Oh, another one. Okay, calculate the y component. Okay. So he's got to have another for this, the z component. So what he's doing,
after you do this, you're going to have an x component, a y component, and a z component. He wants you to enter the x component somewhere, the y component somewhere else, and the z component somewhere else. Which seems strange because a minute ago
he wanted you to enter a vector like that, fx, fy, fz. This is a vector 2, mx, my, and mz, but he wants you to enter it in 3 different locations. Why? I don't know. Okay, this one's a straight up kind of thing. F1 and F2, entered at some weird location. Determine the moment of O of force, about O, the force F1. So all that is that's just the straight out application of this same equation, which is R cross F. Find your R, cross it with whatever F is, which he gave you. And then you get the answer to the first one and the answer to the second one. And then I am thinking he probably is going to have multiple. Yeah, there's a bunch of them. But again, he's breaking the moments into individual parts to answer, which is okay. That's all right. There's your moment R, another moment. Oh, there's an alpha. Oh, he's really getting you there. Well, so I think we're close to time, and I don't expect myself to be, I don't know, so don't be surprised if you get an email that says we're going to do an online session, so, or I'll put some videos or something. It's just one of those things, you know. I don't think I have COVID because testing and all that, but testing sometimes doesn't work right. So in the meantime, we're just existing. So, oh yeah. So do you want me to? Okay, hang on. Let me cut this off.